There we go. Now it should be good. Okay, PSO. So again, I'm going to leave these in this view. I realize it might be annoying, but it's because I have notes, and otherwise I can't see the notes I have for myself. These slides are adapted from slides from a buddy of mine, Kyle Harrison. So FYI, giving him credit. The particle swarm optimization is part of a much bigger, broader category called swarm intelligence, which is part of computational or evolutionary computation, which is part of computational intelligence, but there's a lot of layers to this. So we have PSO, which is a type of swarm optimization, which is a type of evolutionary computation. A GA, for example, is the type of evolutionary algorithm that's a part of evolutionary computation. Long story short about all that, though, is there's a lot of categories that kind of get down to the same general ideas. At the end of the day, we can almost think of our GAs kind of as swarm intelligence, and vice versa. We can kind of think of our PSO algorithm kind of as a GA as well. You just have to kind of consider how we're modifying things. Like, okay, well, what are the genetic operators? How is selection? All those types of questions. The boundaries get fuzzy. Because remember how I've been talking, like everything in evolutionary computation is not nearly as well defined as you might think or expect, compared to other fields of computer science even. Everything's kind of like, just here's an idea, go with it. If you didn't gather that yet so far. All right, PSO. So, I don't know, the story goes, someone was watching a flock of birds or fish or something, and they're like, huh, you know, it's interesting. Maybe those birds are avoiding a predator or something, or maybe they're pursuing food, I don't know. But there's some sort of organization going on there, right? Clearly you can see. They move together, kind of like as a unit, but at the same time they're also kind of operating independently because they don't want to bump into each other. So no individual in there, no individual bird is making a decision for the whole group. It just kind of happens that way. So the story goes, someone was looking at this going like, oh, that's interesting. And it works pretty well in terms of them moving about, finding things, whatever. There's this weird like group dynamic and individual dynamic at play. And it's neat because ultimately at the end of the day, they're all doing their own thing. They're reacting to the individuals right around them, but they're still all doing their own thing. So these particles move towards the areas it likes the most, they like the most. Whatever that means. We'll talk about what that means in the context of evolutionary computation. But the particles also have this propensity to move towards areas the population likes as well. So I'm interested in going where I want to go, but I'm also influenced by that group dynamic. So in the context of evolutionary computation, you know, maybe I as a particle am moving through space, right? But my whole swarm has seen a really good solution over there. And I'm doing my own thing, but I kind of know that, like, well, there is a good one over there. So I'm influenced by that information, but I'm still making my own decisions. And depending on what level we want to get into for how all the communication and what's being communicated, what's being remembered, there's a lot of things we could do here. Swarm intelligence, same general idea as an EA, where it's like, here's just a bunch of ideas, go, do whatever you want. If anyone tries to tell you, no, there's a well-defined set of, no, there's not. There's a building block and you just try different ideas and you go, you have fun. See if something works. We could do it where individuals do their own thing and they're influenced by the big group dynamic. Or you could go like, okay, individuals are affected by their own decisions, the group dynamic, but also those that are around me as well. There's a lot of things you could do. But we have these individuals operating, but they're also influenced by layers, possibly multiple layers of other forms of influence. So for optimization perspective, each particle moves towards the best area it has seen, while also having a propensity towards moving towards the best place any particle in the whole swarm has seen. At this stage, it may be obvious, maybe not. At this stage, you may be thinking, okay, how is this making sense in the context of TSP? Well, chances are you're not going to use something like PSO for TSP. We like PSO for things with real values, like continuous spaces, because it works really well like that. We can use a GA that can work with continuous values, but they tend to suck. We've got some ideas and strategies that make them work decently well. A PSO kind of does a really good job of working with continuous spaces. So, at the back, can you see that reasonably well? So what do we have? This is, from these two simple rules, we get interesting complex behavior. All right, so emergence of complex behavior from simple rules. It looks like this is a minimization problem. It's kind of like a topography map, right? So like we've got this multi-dimensional space. It's got an X, a Y, and a Z, but the Z's kind of like we're looking top down. Right? We've seen topography maps before, right? Yeah.
When you say a real value for PSO, do you mean like real as in the mathematical sense?
Yes, like a continuous thing. Yeah. So here, the yellow parts are high. And I guess this is a minimization problem. But we can see that this landscape, this three-dimensional landscape, it's kind of like it's bouncy, right? Like yellow is really high, and then we have these lower spots, but then we've got even lower spots and lower spots. So we've kind of got these like little dips. And we can see the particles, they all start in arbitrary locations, and you can even see their vector. So let's see it restart. So you can see the vector and how much they're moving towards a certain location. Here, they want to find the smallest thing, but each particle is also influenced by the best thing it's seen so far. So keep your eye on this one right here. When it restarts, look at the top left, and you kind of see how it kind of just goes like, no, I'm going to hang out here. Because it's really affected by what it saw. But you can see it's getting kind of pulled towards the others because it's influenced by the others. So it starts, we've got this 3D thing, and it looks like these points are looking to find the lowest value, something around -5, I guess. Cool? Was that a question back there, or just a... Cool. So typically, our representation for a particle is going to be a vector in the space. If it's a 2D space, it's a two-dimensional vector. It's a 2D point. If it's three-dimensional, it's three-dimensional. Four-dimensional, four-dimensional, and so on. Typically, this is going to be a rather indirect encoding. It gets decoded to mean something. For example, I mean, a lot of time, like what you're going to do for the assignment will be, like, take a toy problem. Okay, there's some classic toy problems that are defined. You get this three-dimensional space that you want to find the smallest point in it. But you can go to like Google. I think I'll give you some examples in the assignment description of like where to go to find example problems. You find a mathematical function that describes the space, and then you tell your particles to try to find the smallest point in that, defined by that function. So, sure, in that case, the vector represents the point in the three-dimensional space. But if we're dealing with continuous values, like if we're applying it to a real-world problem, sure, it's always going to be a point in that high-dimensional space. But what a point in that high-dimensional space means will depend on the specific problem. Okay, this, if at any point you're like, I hated physics, I hated symbols like this, don't worry, this is far, you're overthinking it, it's this type of computer scientists, we don't like scary symbols. This is the extreme. So we've got x and v. X, the position in space at a given time. V, the velocity of the particle at a given time. And then the P best is the particles known best, and then the G is the global or group or swarm known best position. So each particle knows this information about themselves for each time step. So typically all particles are connected in terms of like, well, every particle knows what the global one is, but there's nothing saying you couldn't design it where it's like, well, what if we had like two separate groups where each particle can only know the best of their own group and not the other group? Or what if you had like two, but then they know the best of their own group and the other one, but it affects how much I'm affected? All of these decisions, whatever the hell you want. It's yours to play with. So just have certain yeah, okay, whatever. So velocity update is usually done with this equation here. The velocity at time plus 1 is going to be some variable, omega, that's omega, right? Lowercase omega? Yeah. Lowercase omega, it's typically going to be between 0 and 1. Almost always. So you take some proportion of my speed from the last time. That's kind of like a momentum, or I guess they call it inertia. How much am I likely to stay on my current trajectory? But there's these other terms that kind of influence where it wants me to go. So part of it is, okay, I'm going to take the C1 value and do, okay, P best minus where I currently am. Basically how far away I am from what I've seen as my best, and how far away I am from what the group is seen as the best. So the further away I get, the more I'm kind of like pulled towards it. Yeah?
So from looking, when you showed the graph, like with all the particles kind of swarming towards the middle, I know we're like talking about it in like physics terms, but did you also think of it in terms of like a differential equation with like polarity?
You could, but good luck when you've got all these particles, because this is a complex system. And you're going to have a lot of particles influencing a lot of other particles. And you might say, well, you know, if you think about it like this, at any given point in time, if I know the starting conditions, I can simulate everything perfectly and know where everything will be at any given point in time based on how they influence each other. But good luck, right? It kind of goes back to that same idea as cellular automaton. Remember that game of life thing we were looking at earlier in the semester? Given the starting conditions, you can simulate it, but even though it follows such simple little rules, once you kind of put it together in aggregate, it gets so big and so complex that you can't actually say, well, at time whatever, I know it's going to look like this, unless you run that execution. Okay. So yeah, you could, but I wouldn't. Okay, so then we have this C1 and R1. Okay, so C1 is some value that they call like the introvert thing. The bigger this value, the more I'm going to be influenced to be pulled towards the best thing I've seen. And what else we have? We've got R1, okay, influence of the personal best known possible velocity. High C1 makes introvert particle, yeah, okay. And hold on, now I'm forgetting what R1 and R2 are. Ah, yes, I get to those, okay. And then C2 is the extrovert because it's the one that affects the global best value. So the bigger the extrovert measure, C2, the more I'm going to be pulled towards the group best. Questions about this so far? Yes?
Does it mean it's more if the particle is affected by the best, not so much the particle affects the best even though it's less, but for the extrovert part?
So yeah, the introvert is, if that C1 is bigger, and the best thing I've seen is there, but the best thing the group has seen is over there, I'm still pulled, like there's a bigger influence of this
Yeah.
on me, but the extrovert is the opposite then. Where it's like, the best I've seen is here, but I really want to go towards that group one. And these are parameters I tune.
I just,
So, carry on.
I just mean that we're talking about like the global best affecting the particle, not the particle affecting the global best.
Yes, yeah, this is the particle speed update. Yes. So the global affects me. Now, if me as a particle, we're going to get there, if me as a particle finds a new best, well, that'll update the global best. But that's kind of like a consequence of the whole system. And then we have these random or stochastic components. Now here's where it gets a problem if you want to start simulating it deterministically. Well, we've got this stochastic part where we are going to get some randomness involved. It'll be between 0 and 1, I guess. And we like this randomness because if every time we hit run it ends up in the same position, okay, great. But if we add that little bit of random movement, we call it like entropy in the system, then we're more likely maybe not to get stuck at a local optimum. Maybe helps with early convergence. We can start from the exact same starting positions and have different results. Unless, of course, we use the same random seed, but that's a whole other, that's something else. So that's what all these pieces are. The speed at the next time step. And if you're looking at this as a big, long expression, you're thinking about it the wrong way. That's how we implement it. That's how we do the calculation. But my speed update, where I'm going, my trajectory, is based on 3 different parts. The one part is my inertia. Where was I going before? Right? If I'm running full steam that way, and I want to go that way, I can't turn on a dime, right? I've got that momentum. I've got that behind me. So that affects the particle speed. Another thing that affects the particle speed and trajectory is I do have that propensity to move towards the best thing I've seen so far. So if I'm running that way, but the best thing I've seen so far is here, I'm going to start kind of like turning like this. But if the best thing everyone's seen so far, the extrovert portion, is over there, that's also going to affect my trajectory as well. So don't think of the math as the thing that we care about. Obviously we do, but the math is describing the idea. The math is describing the intuition there. And that's a great way to do it. You can do it with other math if you want. You can try whatever the hell you want. But this is fairly typical. Okay, what are normal settings? Don't ask me how or why, but apparently some guy named Vandenberg showed the parameters omega of 0.729844 and C1 and C2 both being 1.496180 of working really well. So for whatever reason, these are great starting points. I'm not a big PSO person, so I don't really feel comfortable going, what the hell? Like, that seems like nonsense to me, but I'll trust him because that's what the experts say. Yeah.
And omega is just the momentum constant?
Yeah, the inertia, yeah. Effectively, yes. So there we go. And it looks like with this designation, if we have C1 being C2, I am equally affected by the global and my best as well. But we can change that. There's nothing saying we have to go with these values. It's just they were shown to be good. Anyone else find that kind of silly? I certainly do. Oh, here's some great values. I proved it. Sure you did, but whatever. So yeah, Vandenberg, I'll go. Hey, he knows more about this than I do, so I'll go with him. Yep, exactly. All right, so position update, that's just where was I plus the vector. And like if that's my speed, after one time step, I will be there plus where I was going. Okay? Think of it like this. If I'm here and it says each time step I take one step forward in that direction, there, you just add it together. But of course it could be multidimensional, so if it's like add one in that direction and one in that direction, okay, I go here, right? So don't overthink it. Where I is just some arbitrary part. So the algorithm. Initialize particles randomly, initialize velocities to 0, I guess. Well, iteration, max iteration, or stop criteria not met. So basically, iterate until we're happy, kind of like a GA. Remember how GA would say, well, when do you stop it? I don't know, after 1,000,000 generations, after 1,000 generations? Once it's converged, once it hasn't improved, once you find something as good as a certain value, whatever you want. So for each iteration, for all particles, evaluate their fitness, update the personal best, then update the global best once you've done it for everybody. If the global best needs to be updated, of course. Then for all particles, calculate the new velocity and update their position. Do step by step by step by step by step. Cool? Now, if you say, well, why not just, like we've got those 2 for loops, why not kind of combine them? And you know, we could, but if you do it this way, it kind of keeps them separate. Where it's like, okay, everybody moves at once at each step of the simulation. Otherwise, we have like some sort of like in-betweenness, which is weird. Yes?
Is there a way to kind of like break the global best if you were to have like a unique optimum that every single particle got stuck in itself? So like if every particle itself got stuck in its own unique optimum, and then there weren't any like hives together, would there technically be no global optimum?
There would be, because it would be the best of the locals. So the global is just, if you had 100 particles, and then we were minimizing, and particle 1 got stuck in a hole of -1, particle 2 at -2, and so on and so on and so on, they're all stuck in their own personal bests, but the global optimum is still going to be -100. Does that answer your question?
Yeah.
Cool. Now, again, this is the starting point. This is here is your basic, simple, straightforward implementation. Don't do that, but this is your starting point. This is where you go, okay, but I want to have like subgroups that have it. And I want to have the particles have some sort of detraction from one another, right? Because you figure those birds are flying, but they don't crash into each other. So maybe you've got this like propelling phenomenon. In fact, a buddy of mine, I don't know if it was very novel, because this was going back to grad school, but a buddy of mine, so the guy Kyle Harrison and this other guy, they were, trying to remember their name, I think Madison something, I can't remember, but anyways, Kyle and Madison were working on PSO, and they actually worked with Engelbrecht, who's actually one of like the big important researchers in the world, if not the top, one of the top people in PSO. They were doing all these experiments and they weren't getting really good results, and then Madison just said like, well, what happens, they were doing a simulation of people evacuating a building or something for some reason, and one of the terms in that simulation is, well, people kind of avoid each other. Like if we're running out that door, if it's not a panic scenario, you know, I'm not going to run out the door such that I bop into everybody. I'm going to run to kind of like avoid running into you and them, right? You know, in a crowd, we're not all like this all the time. We kind of keep our own space, right? So Madison thought, well, why don't we make that part of the thing where like the particles kind of, you know, they move together, but they've kind of got that little bit lower of a repelling, and the results went crazy good all of a sudden. So it's just, sometimes even the simplest idea can make the world of difference, which is really cool. Yeah?
Ryan Lukeman has a simulation that maps like bird flight patterns.
Yeah?
Yeah. That's
Use that then. Use his for PSO and see what happens.
well, it's written in MATLAB, so.
Well, fix it. Of course I'm being silly. MATLAB is fantastic. But we've got the obligatory MATLAB steps, right? So, of course it doesn't. Just they start counting at 1. What? Who starts counting at 1?
R does?
R does? Yeah, I know. What the heck? R is equally trouble. We count from 0.
Double trouble.
Double, yeah. All right, so anyways, that's it. That is it. And if you're thinking, whoa, that's complicated, you're overthinking it. It is calculate the difference between vectors. Who here is using Python? If you use NumPy arrays and you do the difference between NumPy arrays, what do you get? The vector difference. Like you get like the unit-wise difference. Done. Perfect. What happens if you multiply a NumPy array with a scalar? It just multiplies everything by it. Python will make this so easy. Python will make this like 2 lines of code. And if you're thinking, wait, no, it's you're overthinking it. Slow it down. It's actually rather simple. But raise your hand if you've been thinking so far this semester, you know, I don't know, it feels kind of like, and look, I realize that you're learning these things for the first time, and for the assignments, you're having to go build it for the first time. But when you look back at the GAA assignment, for example, raise your hand if you think like, really at the end of the day, it's only a couple of very simple little rules that we put together and hit run. Because that's what it is. It's just all these little simple rules, but they work. To me, that's where I start to have fun. To me, I love when it's like, you know, from such a simple set of rules, something that anyone can understand, like the game of life. If 2 cells around you are alive, then you become alive. If 3 around you, then, you know, very simple rules. You can tell a 4-year-old and they'd be like, okay, cool. But from that, you can get such insane complexity that you can simulate a Turing machine, thereby simulating the game of life, which can simulate the game of life, which can simulate the game of life, which can, isn't that, to me, that's so crazy. With such simple rules, very simple, we get an exceptionally powerful problem-solving technique. Remember, we are not using PSO to solve a problem that a decision tree would make sense for, where k-means make sense for. K-nearest neighbors is probably a better one. We don't use them for those. We use these types of algorithms when it's like, I've got this crazy thing and I want to find a good point in this high-dimensional space, whatever your space is. And I've tried, I've thrown everything at it that I could think of and I don't get good results. Try this. These are the big guns, but the big guns are so simple. And that's why I like them. Because if they were any more complex, I couldn't do them. All right. So yeah, that's the algorithm. Did you say something?
I was murmuring to myself, is that why you tell us not to overthink these assignments?
Yeah, don't overthink it. Remember, computer scientists are stupid. We can only do things step by step by step. If anyone tries to tell us to do 2 steps at once, we fall apart. Right? That's what I keep telling the first-year students. Don't overthink it. When I say what's happening on that line of code, don't be like, well, you know, this function does... No. You're trying to be too smart. Tell me line by line. And then they roll their eyes going like, oh, you're being really facetious. No. That is how you do it. Don't make assumptions, right? That's the same idea here. Does anyone have, by the way, does anyone have an old GPU that they've got lying around they don't have anymore? I found out yesterday my Ubuntu kernel updated to 5.10. And of course, my 2008 GPU was end-of-lifed. And I can't get it to work, and so now my awesome, big, powerful computer with a 2008 GPU in it doesn't work anymore. So if anyone has one kicking around, let me know, because I desperately need one.
This is my only GPU.
That's your only GPU? Well, all right. Anyways, and if you're like, yeah, I've got an old blah, blah, blah from last year, I'll sell it to you. No. You're thinking, no. I need, like, if you have one from, like, instead of 12 years ago, 7 years ago, I'll take it off your hands for you. Anyways, PSO, simple to implement, does not mean weak, does not mean uninteresting, simple to implement, especially compared to other forms of computational intelligence. What's easier to do? Even though you've never written a PSO before, what do you think is easier? Go implement your crazy neural network, and even now with TensorFlow, you know, it's kind of like, oh, I've got to figure it all out. Or a couple lines of NumPy differences, right? A couple lines of NumPy differences. but this works pretty darn well. Computationally cheap compared to a lot of other forms as well. If you've got a GA, you want to do 1,000,000 generations, or 1,000 individuals in each of them. Well, what's 1,000 times? Well, you got to do 1,000,000,000. Now you got to do 1,000,000,000 calculations. This isn't too bad. What else? Small numbers of parameters to tune. This is a big one. With a GA. Okay, what type of selection are we going to do? Tournament. Okay, what's your tournament size? How many generations? What crossover are you going to do? 2-point crossover? How are you going to do? There's a lot of questions to ask. Here, what's your omega? What's your C1 and what's your C2? And hell, they give you good ones to start with. You don't even need to do much tuning. It's fantastic. It's easy to parallelize. You just have each thing go do its thing. I'm going to warn you, though, I haven't really put too much think about it with GPU. This is an old statement before CUDA was a thing. I'm sure it could be offloaded to GPUs somehow, but I haven't really thought about it. It's easy to extend, given the simplicity of the algorithm, it's easy to say, my shoe just broke. It's easy to say, that part. It's been falling off for a while.
I was going to make a joke about it being a sticky note.
Yeah, every time I walk, it goes like flip-flop.
I've been watching it.
You've been watching, it's that distracting. So yeah, it's easy to extend because each thing is just, it's so simple. It's, okay, what if I have this other term where I have it also affected by, okay, great, add on a C3 value with some randomness and the difference between that and something else. Whatever you want. The most common addition, and I know you might be thinking like, well, how is that an addition to? No, it is. If you've got a search space that is defined by some mathematical function, the range of those values can be huge, right? But if realistically, if I'm looking top down, think of that example from before. I'll just go back to that. This one. I'm only looking at the space between -3 and 3, -3 and 3, and -5 and +20, I guess. But that function that describes that space, God knows what it is. Like, I could say, well, what about -7? Right? And the particles can go explore over there. But if you don't really care about that part of the space, you have like your bounded PSO, where you say, like, okay, no, you can't go past here. How you go about doing that, entirely up to you. Maybe you'll make it so if they go really far that way, they come out on the other side. I don't know. Maybe if they do, they get penalized some way. Maybe if they do, they just get sucked back this way or something. Whatever you want. But you can set these constraints. There, great. Bounded PSO, great way to have your constraints. Any of these ideas, whatever. And it's really good for continuous spaces. This is your back pocket idea. Don't use a GA. Because here's the funny thing. When people, if a number of my evolutionary computation colleagues watch this video, I'm going to anger 50% of them. No, I'll anger all of them. Because here's what happens. What I'll do is, if I've got a GA and I want it to work on continuous spaces, I'm going to need to start getting fancy about how my genetic operators work and all this. And I'm going to keep making all these changes. And at the end of the day, when I hit run and I finally get a really good working GA for continuous spaces, I'm painting with a broad brush here. But at the end of the day, after I've done all that, really what I have is just a shitty PSO. Conversely, if I've got a PSO and they're like, no, PSO is great for discrete spaces. All you have to do is change this, and next thing you know, you work towards just a really shitty GA. So typically, don't use a GA for continuous spaces. Now, there are other strategies that work for continuous spaces, like differential evolution. There's a number of other things. Is anyone in here doing a thing on differential evolution? I think someone is. You are. Yeah, perfect. So we'll learn all about that. But anyways. So why not to use it? Well, it can be hard to come up with a good representation for a problem sometimes. It does get stuck in local optimum, and it's not great for discrete problems like I just talked about. But again, we have ideas to deal with these. Enhancement, neighborhoods. This is the idea of having like subgroups. So we'd have an additional term. So we've got swarms influenced by their neighborhood, which is influenced by their global. So they have their introvert, extrovert, and mesovert effects, whatever. Meso, like in between.
I thought it was ambiverted.
Apply local optimization at various stages. This is a good one. Sometimes people call this like mimetic algorithms, where you kind of like combine the two where, look, if I'm doing, just one sec, if I'm doing something like, okay, raise your hand if you've worked on the symbolic regression so far. Okay, here's what symbolic regression really sucks at. It's fine-tuning values, especially if you're dealing with floating point numbers. Because of the way it changes floating point numbers. Your genetic operators, how they're going to change, what those floating point numbers can be, really suck. But something like your simple linear regression follows a nice, very simple mathematical way to just kind of make these nice steps towards the optimal floating point number. Optimal decimal number that fits something. So the problem is, GP for symbolic regression is really good with coming up with these complex functions, like the shape of them, but the value of the constants, they really suck at getting it. So people will kind of do like a let's do a best of both worlds thing, where we get really close to what we're looking for, and then maybe we come up with another strategy for fine-tuning those other values later. Boundary positioning clamping, velocity clamping. Velocity clamping is good. You basically set a limit for how fast a particle can be moving. Because you imagine if you end up with a particle that somehow gets way out here, but it wants to be over there, the amount it's affected by the global position is proportional to the difference it is away from it. So it's going to start to get sucked really fast back that way, and then the particles are flying all over the place. So you set limits on that. Multi-objective, it's really cool for multi-objective problems as well. Here we go, test functions for optimization. Test functions for optimization. I love that Wikipedia has a page for this. So, here's some of them. But here's a bunch of functions. Ooh, the Acme function's a fun one. So, basically, you get a function that describes these spaces, right? And if you want to minimize, great. But here's the thing, look at this one. Like you can see, okay, the sphere function, if your PSO can't find a damn good result for the sphere function, you need to reconsider your life because it is concave. It is so, like your PSO, there's nothing to get stuck in. Your particles are just going to go, oh, wow, okay, there, and it just gets stuck at the bottom and it'll be happy. You'll have all these particles dancing around the bottom of the sphere. Great. So if your PSO can't do that, your PSO sucks really bad. It better be able to do that. But once you start to look at some of these other crazy functions, like look at these ones. It might be kind of hard to tell, but it's very jagged. So every low point is surrounded by a really bad high point. So I might get stuck in that valley really easily. This one, oh, look at this one. This one would be hard for PSO. This one would, I don't even know what the hell that is. But look at these things. Egg holder function. Yeah, I get why it's named that. You can see how the particles can get stuck in those valleys. Right? And every time it makes a step towards getting out of that valley, it's going to go, oh, but I'm worse than I was. And I'm going to start getting sucked back towards where I was. Same idea that we saw here, right? How this guy right here, it's stuck. This is the best. But this is like a top-down view of something similar to that egg holder, right? Where you've got all of these dips, but then like the particles can get stuck in a dip. And although it's affected by the global, it's still, because it's affected so much by where it was, it's stuck there. Any questions about any of this? Yes, oh right, you had your hand up a while ago.
For the idea of neighborhoods, I know we talked earlier in the semester about
What do you think?
Probably, yeah.
Yeah! The answer to could you do is 99.999% of the time, if you've got your head on straight, yes. I mean, if you're asking like, could I run this on my shoes? Well, no. But if you ask any question in the realm of reasonableness, the answer is going to be, yeah, try it. And it's funny, because almost always, too, if you're ever thinking like, oh, this idea is kind of out there, that's sometimes where you find the most interesting results. Never, I sound like a broken record, never be shy about trying your weird idea. Because your weird idea might be fantastic. You don't know until you try, and you'll find out empirically. And at no other point in your lives, you're doing something rigorous like a university course, okay? Once you get a job or whatever, your boss is going to show up and be like, what the hell are you doing wasting our time doing that dumb idea? You have the luxury of trying your dumb ideas and just seeing what happens, because you never know. Take advantage of it. Try the crazy ideas. Implementing a PSO, you could all do that. But if all you do is implement the PSO and you submit it, you're not going to do very well. Like, sure, you'll get your marks, but you're not getting any of those extra points available to you. That's where you have fun. That's where the creativity comes in. Take advantage of your ability to do it now. Cool? All right. I'll see y'all later.